Right now, without you feeling a single thing, without any alarm going off anywhere on Earth, our entire galaxy, the Milky Way, 400 billion stars, every planet, every ocean, every living thing that has ever existed, is hurtling through space at over 1 million miles per hour. And for decades, astronomers had absolutely no idea what was pulling us. Then they found it. A gravitational anomaly so massive it was bending the paths of hundreds of thousands of galaxies at once. Something lurking behind the thickest part of our own galaxy, invisible to us, hidden like something the universe deliberately didn't want us to see. They called it the Great Attractor, and then, just when they thought they finally understood the force pulling our galaxy across the cosmos, they discovered something else entirely. Something on the opposite side of the sky. Not a pull, a push. A vast region of almost pure emptiness, actively repelling our galaxy, shoving us through space as hard as the Great Attractor is dragging us. Two forces, one invisible, one on each side of us, and we only discovered the second one in 2017. This is the story of how we figured out that our galaxy is caught between a monster we can barely see, and a void we almost missed entirely. If you're new here, this channel exists to go deep on the parts of the universe that don't get enough attention. If that sounds like your kind of thing, subscribing really does help the channel more than you might think. It's free and it keeps this work going. Now, let's talk about motion. Here's something most people don't fully grasp about the universe we live in. Everything is moving, not just a little. Everything is in constant, violent, multi-layered motion, all at the same time, all in different directions, stacked on top of each other like frequencies. You're sitting still right now, or maybe you're on a commute somewhere, but your body is spinning with the Earth at roughly 1,000 miles per hour at the equator. The Earth is orbiting the Sun at about 67,000 miles per hour. The Sun is orbiting the centre of the Milky Way at about 514,000 miles per hour, and the Milky Way itself is moving through the universe at speeds that dwarf all of those combined. For a long time, measuring that last part, the actual motion of the Milky Way through the cosmos, seemed almost philosophically impossible. You can't step outside our galaxy and watch it move. You can't set up a speed camera next to the universe and clock us. To measure how fast something is moving, you need a reference point. And for a while, we didn't have a good one. Then astronomers found one. The cosmic microwave background. The faint glow of radiation left over from the Big Bang, filling the entire universe with near-perfect uniformity. If you're moving relative to this background, the radiation in front of you gets slightly blue-shifted, slightly hotter. The radiation behind you gets slightly red-shifted, slightly cooler. It's the same Doppler effect that makes an ambulance siren change pitch as it passes you. Except instead of sound, it's the oldest light in the universe. When astronomers applied this measurement, what they found was unsettling. The Milky Way, along with the entire local group of galaxies, is moving at approximately 600 kilometers per second. That's about 1.34 million miles per hour, toward a specific point in the sky. 600 kilometers per second is not a gentle drift. It's not a coincidence of geometry. Something is pulling us. Something big. And when astronomers looked at where we were headed, they found themselves staring into one of the most frustrating obstacles in all of astronomy. They were looking straight into the Zone of Avoidance. Here's a problem that doesn't get nearly enough attention outside of astronomy circles. We are blind to roughly 20% of the entire sky, not metaphorically, literally blind. The Milky Way is a disk of stars, gas and dust, and we're embedded inside it. When we look in the direction of the galactic plane, along the disk, we're looking through the densest concentration of matter in our galaxy. Stars so thick they blur together. Dust clouds that absorb and scatter light across virtually every wavelength. It's like trying to see the street outside from inside a building with no windows on that side, surrounded by walls of fog. Astronomers call this region the Zone of Avoidance, not because they're scared of it, because for most of the 20th century you simply couldn't do useful astronomy there. Galaxy catalogues just went blank. The most comprehensive maps of the universe had a gaping, irregular hole punched right through the middle, exactly where our own galaxy got in the way. And that's precisely where the thing pulling us appeared to be hiding. In the 1970s and early 1980s, astronomers were systematically measuring the velocities of galaxies, not just whether they were moving away from us, but whether they were moving faster or slower than expansion alone would predict. If a galaxy is moving faster toward a particular region than Hubble's law would suggest, something in that region must have extra gravitational pull. What they found became known as the Great Attractor, a region in the direction of the constellation Centaurus, centered roughly 250 million light-years away, toward which enormous numbers of galaxies, hundreds of thousands of them across a region of space hundreds of millions of light-years across, appeared to be flowing. The numbers were staggering. Whatever this was, it had to be generating the gravitational influence of tens of thousands of galaxies, a supercluster of superclusters, a gravitational basin so deep it was warping the flow of matter across the entire local universe. But it was sitting almost dead center in the zone of avoidance. They knew something enormous was there. They couldn't see it. This is where I want to pause for a second, because I think this moment in the history of astronomy is genuinely one of the strangest positions science has ever been in. We had measured the shadow of something, the effect its gravity was having on hundreds of thousands of galaxies across hundreds of millions of light-years, without being able to observe the thing itself, like discovering the footprint of a creature you can't find. And what did that footprint imply about the size of whatever made it? The answer kept changing, and every time it changed it got stranger. Through the 1980s, the Great Attractor became one of the most exciting concepts in cosmology. Early estimates suggested it might require the mass of tens of millions of billion suns concentrated in one region. The press went wild with it. What was this thing? A collapsed megastructure? A region of anomalous density left over from the Big Bang? Then, in the early 1990s, something unexpected happened. Astronomers started getting better data, and the better the data got, the more the Great Attractor seemed to shrink. A 1992 study, the most comprehensive large-scale velocity survey done to that point, found that a significant portion of the anomalous motion previously attributed to the Great Attractor appeared to be a statistical artifact. Something called Malmquist bias had been inflating the apparent concentration of galaxies in that direction. When you observe galaxies at large distances, you tend to preferentially see the brightest ones, which clusters in certain directions can mimic. Strip that out, and the Great Attractor's pull didn't look as insane as it once had. But it didn't go away. The motion was still there. Something was still pulling everything, and then X-ray telescopes gave us what optical telescopes couldn't. By the mid-1990s, surveys using the Rosat satellite started successfully piercing through the zone of avoidance. Not perfectly, but enough. What they found was the Norma Cluster, a massive, rich cluster of galaxies sitting almost exactly where calculations predicted the centre of the Great Attractor would be. Also called Abell 3627, it's one of the most massive galaxy clusters in the observable universe, containing thousands of galaxies embedded in an enormous cloud of hot gas visible in X-rays. So that was it. The mystery was solved. A big cluster, hiding behind our galaxy's disk, case closed. Except, and there's always an except, the Norma Cluster alone wasn't massive enough to explain the full motion either. And then, astronomers found something even bigger. Here's something that exposes a deep assumption we make about the universe without even realizing it. When we think about cosmic gravity, about what's pulling what, we tend to imagine discrete objects. A cluster pulling on a cluster, a supercluster pulling on smaller structures nearby. But the universe doesn't work in neat, contained units. Gravity has no range limit. Everything in the universe is technically, gravitationally influenced by everything else. At large enough scales, the structures you see determine flows of matter across billions of light years. And when astronomers started mapping the universe at those scales, they discovered that the Norma Cluster, as massive as it is sits inside something much, much larger. The Centaurus Supercluster, the Hydra Centaurus Supercluster, and beyond that, the Shapley Supercluster, the most massive concentration of galaxies within roughly 650 million light-years of Earth, named after Harlow Shapley, who first noticed the concentration of galaxies there in the 1930s but had no context to understand what he was looking at. The Shapley Supercluster contains dozens of galaxy clusters, tens of thousands of individual galaxies, and a gravitational mass so colossal that it has a measurable effect on galactic flows hundreds of millions of light-years away. When astronomers ran the numbers, they found that Shapley alone accounts for a significant fraction, maybe a quarter to a third, of our galaxy's total peculiar velocity. So now the picture was this. The Milky Way is being pulled by the Norma Cluster, which is itself part of a larger supercluster structure, which is being pulled and simultaneously attracting us towards Shapley, which sits hundreds of millions of light-years beyond the Great Attractor zone. The Great Attractor wasn't one thing. It was a whole cascade of gravitational influence, each layer nested inside a larger one, each one tugging our galaxy along a path that stretched across hundreds of millions of light-years. But here's where the story takes a turn that no one saw coming. In 2014, a team of astronomers led by R. Brent Tully at the University of Hawaii published a paper in Nature that reframed everything. They weren't just studying where galaxies were, they were studying how galaxies were moving. Peculiar velocities, the deviation from pure Hubble expansion, trace the underlying gravitational landscape like water tracing the topography of a landscape. If you map where all the rivers are flowing, you can reconstruct the mountains and valleys that shaped them. When Tully's team did this for tens of thousands of galaxies across hundreds of millions of light-years, they found something beautiful and terrifying at the same time. They found a basin. Think of it like this. Imagine you could look at the entire surface of a continent from above, and instead of seeing the geography, you could see every river, every stream, every trickle of water, all at once. The pattern of where water flows tells you everything about the landscape underneath, where the valleys are, where the ridges are, where water collects. Now do that with galaxies. Replace water with galaxies. Replace topography with gravity. Replace rivers with the large-scale flows of matter through the universe. When Tully's team did this, using data from thousands of galaxy velocity measurements compiled over decades, what emerged was the outline of a single gravitational basin, a vast region of space where all the galaxy flows converged inward toward a single gravitational low point. They named this basin Laniakea, a Hawaiian word meaning immeasurable heaven. Laniakea is a supercluster, our supercluster. It's the cosmic structure that the Milky Way calls home, and it's enormous. It spans roughly 520 million light-years across, contains the mass of 100 million billion suns, and holds about 100,000 galaxies, including the Milky Way, the Andromeda Galaxy, the Virgo Supercluster, the Great Attractor region, and the Norma Cluster, all nested inside this single gravitational basin. When you see the visualization of Laniakea, and if you haven't seen it, go find it immediately. It might be the most beautiful piece of scientific visualization ever made. You see the Milky Way as a tiny dot on the very edge of this structure, and you see every galaxy in the basin flowing inward, like rivers draining toward a central point. The Great Attractor isn't a discrete object sitting somewhere. It's the gravitational attractor point of the entire basin we live in. This reframing is profound. We're not being pulled toward the Great Attractor from outside. We live inside the Great Attractor's sphere of influence. The Milky Way is on the rim of Laniakea, slowly spiraling inward toward the core, caught in a gravitational whirlpool that's been pulling galaxies toward its center for billions of years. And now, finally, we can ask the question that has been sitting underneath this entire story since the beginning. If we know what's pulling us, why are we still moving so fast? The Laniakea Basin is massive, but is it massive enough to explain a 600 kilometers per second peculiar velocity entirely? When astronomers ran the numbers more carefully, the honest answer was no, not quite. Something else was contributing to our speed, but not by pulling us, by pushing us. Let me take you back to 2017. A team of researchers, Yehuda Hoffman, Daniel Pomered, Brent Tully, and Hélène Courtois, some of the same people behind the Laniakea discovery, published a paper in Nature Astronomy with a title that barely hints at what they actually found: the Dipole Repeller. Here's the setup. When you model the peculiar velocity field of the universe, the full three-dimensional map of how galaxies are moving beyond what expansion predicts, you're essentially solving for all the gravitational sources and sinks simultaneously. Think of it like reconstructing a landscape from water flow patterns. You can find the mountains because water flows away from them. You can find the valleys because water flows toward them. What this team found was that there was a massive underdensity, a vast region of space containing far fewer galaxies than average, sitting on the opposite side of the sky from the Great Attractor and Shapley. And this underdensity wasn't neutral. It wasn't just a void that happened to be empty. It was actively pushing. The mechanism is subtle but real. In a universe where the average density of matter is roughly uniform, a void, a region with less than average matter, exerts a net gravitational push on surrounding structures. Not because voids have negative gravity, because the absence of pull in one direction is effectively a push relative to the pull everywhere else. Galaxies on the edge of a void experience stronger gravitational attraction from the denser regions around the void, causing them to flow away from the void center. The Dipole Repeller is a void roughly 600 million light-years across, located in the direction of the constellation Gemini, almost directly opposite the Great Attractor in the sky. And when the team modelled its effect, they found something striking. The Dipole Repeller wasn't just a footnote to the Laniakea story, it was contributing as much to our galaxy's peculiar velocity as the Laniakea Attractor itself. Half our cosmic speed comes from being pulled toward the Great Attractor, half comes from being pushed away from the Dipole Repeller. This is the part that consistently blows my mind. The two forces nearly balance. We're not hurtling through space being overwhelmingly dominated by some single gravitational colossus. We're caught between two roughly equal and opposite forces, one pulling, one pushing, and they together explain why we're moving the way we are. The researchers described it themselves as a story of love and hate, being pulled toward what we love and pushed away from what repels us, in a cosmic tug-of-war that's been playing out across hundreds of millions of years. And the push side of that story is a void, exactly the kind of structure that this channel exists to explore. But let's slow down on the mechanism for a moment, because the how here is not obvious. When most people hear that a void is pushing galaxies, the natural question is, how does empty space push anything? Nothing is there. What's doing the pushing? The answer requires letting go of the intuitive picture of gravity as something that only comes from objects, from mass concentrations, from stars and clusters. Gravity in cosmology is a field that permeates all of space. In a perfectly uniform universe, those gravitational fields would cancel out everywhere, no net force in any direction. But the universe is not uniform. It has overdense regions and underdense regions, and in that landscape, what matters isn't just how much mass is pulling you from one direction. It's the imbalance between forces from all directions simultaneously. Imagine you're standing in the middle of a tug-of-war, with teams pulling you from every direction at once. If every team is perfectly balanced, you don't move, but remove one team from behind you, replace that side with emptiness, and suddenly you accelerate forward. Not because something pushed you, because the net force from every other direction is no longer balanced. The void creates a net displacement toward the opposite side. That's the void repulsion effect. That's what the Dipole Repeller does. And the fact that we could measure it at all is a tribute to one of the most painstaking data sets in modern astronomy. The team used the Cosmic Flows 3 catalogue, a compilation of over 18,000 galaxy peculiar velocities assembled over years by Courtois and Tully's group at the University of Hawaii. Building that catalogue required measuring the distances to thousands of galaxies using multiple independent methods, cross-checking them against each other and stripping out all the noise until what remained was the true peculiar velocity signal. The Dipole Repeller didn't show up in smaller datasets. It only became visible when the sample was large enough and clean enough to reveal a large-scale pattern. Its contribution was quantified at roughly 250 kilometers per second of our total peculiar velocity, comparable in magnitude to the combined pull of the Norma Cluster and the near side of the Shapley Supercluster. It had been there the whole time. We just weren't asking the right question to find it. So what exactly is this thing? What is the Dipole Repeller made of? Or rather, what is it not made of? At its simplest, the Dipole Repeller is a supervoid, a region of space where galaxies are sparse, where matter is thin, where the cosmic web has produced one of its characteristic empty cells. In the large-scale structure of the universe, matter isn't distributed evenly. It's concentrated into filaments and sheets, the cosmic web, with vast, nearly empty voids occupying the space between them. The Dipole Repeller sits in one of these void regions, roughly in the direction of the constellations Gemini and Canis Major. It's not the most prominent void in the universe by volume. That distinction belongs to other candidates we'll talk about in future videos. But it may be the single void with the greatest measurable effect on the motion of our galaxy. Here's something that I find genuinely profound about what this discovery means. For most of human history, voids were the absence of something. Empty space was passive. It didn't do anything, it just was. The interesting stuff happened at the dense end of the universe, in stars and galaxies and clusters, in the places where matter concentrated, but the Dipole Repeller flips that. An emptiness, a place defined entirely by the absence of mass, is one of the primary drivers of our galaxy's motion through the cosmos. Our cosmic address, our velocity, our trajectory through the universe is shaped as much by nothing as it is by something. Before I leave this section, and this connects to something that matters for this whole video, I want to ask you something. When you think about where you are in the universe, what image comes to mind? The Earth in the solar system in the galaxy in some abstract expanse of space? Drop that in the comments. Because I think most people's mental model of our cosmic location is missing two massive pieces, and those are exactly the two things we just found. The pull and the push, the attractor and the repeller. Tell me what your mental model looked like before this video. I read all of them. Now let's talk about what this actually means for our future. But before we do, one more thing about the Dipole Repeller that I think deserves to be said clearly, because it tends to get glossed over in shorter treatments of this topic. The Dipole Repeller is not a perfect emptiness. Nothing in the universe is. Even the most underdense voids still contain some galaxies, just far fewer than average. Where a typical region of space might have several galaxies per cubic megaparsec, the interior of a deep supervoid might have less than 1/10 of that. It's not zero, it's dramatic underdensity. And in cosmological terms, a dramatic underdensity creates effects that are, for practical purposes, indistinguishable from a push. This is actually one of the ways the Dipole Repeller differs from the voids we've talked about in previous videos on this channel. The KBC void, the enormous underdensity we live inside, is primarily interesting as a local phenomenon affecting how we measure the expansion rate of the universe. The Eridanus supervoid is fascinating because of its possible connection to the CMB cold spot. But the Dipole Repeller is interesting for a much more immediate, almost mechanical reason. It's one of the two primary forces currently moving our entire galaxy. It's not an abstract cosmological structure. It's doing something to us right now. There's also the question of how the Dipole Repeller relates to the large-scale structure we've already identified in that region of the sky. The direction of Gemini and Canis Major doesn't correspond neatly to any of the superclusters or voids that have been catalogued in detail. The Dipole Repeller may overlap with several smaller known voids that together create the large coherent underdensity, or it may represent a distinct structure that hasn't been fully mapped at all wavelengths yet. Follow-up surveys are ongoing, and the boundaries of the structure are still being refined. What we know for certain is this: Whatever its exact shape and extent, it's real. It's in the data, and it's one of the defining features of the cosmic neighborhood that shaped everything about where we are and where we're going. Let's come back to something that's been lurking in this story from the beginning, because it deserves more attention than it usually gets. The Zone of Avoidance didn't just delay our understanding of the Great Attractor by a few years. It's a structural limitation on our ability to understand the universe, and it still exists. Optical telescopes are essentially useless in the Zone of Avoidance. The dust and gas of the galactic plane absorbs visible light almost completely in some directions, but other wavelengths penetrate better. Radio waves pass through dust without much trouble. X-rays can pierce the galactic plane. Near-infrared light is less scattered than optical, and since the 1990s, astronomers have been systematically using these wavelengths to map what's behind the galactic curtain. The results have been genuinely surprising. Several significant galaxy clusters have been discovered hiding in the Zone of Avoidance, structures we simply had no idea existed because we'd never been able to look there. Some of these contribute to the gravitational flows we've been talking about. Others may be connected to even larger structures we haven't mapped yet. There's a galaxy cluster called the Vela Supercluster, discovered in 2017, hiding behind the Milky Way's disk. When it was found, astronomers estimated it might contribute significantly to our peculiar velocity, a contribution that hadn't been accounted for in any previous model of our cosmic motion. What this means is that our map of the forces shaping our galaxy's journey through space is still incomplete. Every time we find a new way to see through the Zone of Avoidance, we find something that wasn't in the model. The Great Attractor, for all its decades of study, is still being refined. The Dipole Repeller is new enough that follow-up studies are still being published. We are, in a very real sense, still in the early chapters of understanding why we move the way we do, and the specific discoveries that have come out of Zone of Avoidance research in the last decade are worth dwelling on, because they keep changing the model in ways that nobody predicted. The Vela Supercluster deserves more than a passing mention. It was discovered in 2017 by Renée Cran-Korteweg and her team using near-infrared observations from VISTA, a telescope at the ESO Paranal Observatory, specifically designed to see through dust-heavy environments. What they found was a supercluster comparable in mass to Shapley, hiding behind the galactic plane at roughly 800 million light-years distance. Its existence had been suspected from peculiar velocity patterns that didn't fully add up with known structures, but confirming it required years of observations through one of the most obstructed regions of sky. The contribution of Vela to our peculiar velocity is still being quantified. Some studies suggest it may account for a significant fraction of the motion toward the southern galactic plane that hadn't previously been explained. Others suggest it's real, but its contribution is modest. The surveys needed to settle the question require enormous telescope time, because you're essentially trying to map a supercluster through a fog. Radio astronomy has been transformative here. The Wallaby Survey, the Widefield ASCAP L-band legacy all-sky blind survey, running on the Australian Square Kilometre Array Pathfinder, is systematically mapping the southern sky in the 21 centimetre hydrogen line, which cuts through galactic dust as cleanly as radio waves can. Hydrogen emission traces galaxies regardless of whether you can see them optically. Wallaby is expected to detect tens of millions of galaxies, including enormous numbers hiding in regions previously classified as Zone of Avoidance. Early data releases are already filling in gaps in the velocity field map that Cosmic Flows 3 left open. There's also the ZOE survey program specifically, a decades-long international effort to systematically use X-ray, radio and near-infrared observations to map the hidden sky. Every new release of these surveys produces revisions to our understanding of the local velocity field. The Great Attractor model of 2024 is meaningfully different from the model of 2014, and the model of 2034 will likely be different again. The sky we live under has always had a blind spot. We're only now beginning to see through it. And here's the profound implication for everything we've discussed about the Great Attractor and the Dipole Repeller. Both measurements are only as good as the data that went into them. The Cosmic Flows 3 catalogue that revealed the Dipole Repeller deliberately excluded the Zone of Avoidance region. The galaxy flows in that band of sky simply weren't in the sample. The researchers worked around it, constructing their velocity field model from the visible portions of the sky and extrapolating across the gap. That extrapolation is reasonable. Gravity doesn't suddenly behave differently near the galactic plane, but it means the Dipole Repeller's shape and boundary on one side are inferred, not directly measured. The Zone of Avoidance cuts right across the region between us and the Dipole Repeller in some directions. What's hidden there? Probably not enough to overturn the whole picture, but possibly enough to shift the numbers, to change the shape, to reveal structures that modify the push-pull balance in ways that matter. This is a genuinely open question, and the answer depends on the surveys that are still running, still collecting data, still building the catalogue that will eventually let us look at the full sky without gaps. The Dipole Repeller we found in 2017 is probably a good first approximation of something real. The refined version, 10 years from now, will look different. Our galaxy is moving at 600 kilometers per second toward the Great Attractor region. So are we eventually going to get there? What happens? This is where cosmology delivers one of its most elegant and quietly devastating answers. We will never arrive. The reason isn't that the distance is too great, though it is. The reason is that the universe is expanding. Space itself is growing. The Great Attractor is receding from us as the universe expands, and while gravity is pulling our galaxy toward it, the expansion of space is working in the opposite direction. The Shapley Supercluster, which sits beyond the Great Attractor, is already receding faster than gravity can pull us toward it. We will never reach Shapley. Whether we'll eventually merge with the Norma Cluster region, or whether expansion will win out at that scale too, depends on the future behaviour of dark energy, the force driving the universe's accelerating expansion. And right now, the nature of dark energy is one of the most contested questions in all of physics. New data from the DESI instrument released in 2025 suggests dark energy may be weakening over time, which could eventually change the balance between gravity and expansion in ways we don't fully understand yet. What we do know is this: our motion through space is not random. It is not a coincidence of initial conditions. It is the measurable, observable signature of the large-scale structure of the universe around us, the cosmic web of filaments and voids that gravity and dark energy have been building since the Big Bang. The Milky Way moves the way it moves because of where the matter is and where it isn't, because of a push from a void and a pull toward a basin, balanced against the expansion of everything. There's a useful distinction here that cosmologists make between gravitationally bound structures and unbound ones, and it draws a sharp line through our cosmic future. Gravitationally bound structures are regions where the mutual gravitational attraction between members is strong enough to overcome the expansion of space. The Milky Way and Andromeda are bound. They're actually approaching each other and will collide in roughly 4.5 billion years, eventually merging into a single elliptical galaxy. The local group, the few dozen galaxies we belong to, is bound. Even the Virgo cluster, tens of millions of light years away, exerts enough pull on the local group that we're moving toward it slowly. But Laniakea as a whole, that's a different story. Laniakea is not gravitationally bound. It's a flow basin, a region where the current trajectories of galaxies converge, but not a region where those galaxies are locked together by mutual gravity. Think of it as a momentary snapshot of where things are heading, not a permanent structure. As the universe expands, the outer members of Laniakea will gradually be pulled apart. The cosmic web will stretch. Eventually the basin itself will become irrelevant, as expansion dominates at larger and larger scales. This is where the DESI findings about dark energy become genuinely consequential. If dark energy is weakening, as the 2025 data suggests, then expansion may eventually slow down. That would change the calculation for which structures stay bound and which drift apart. Some structures that cosmologists currently classify as unbound might, in a future with weakened dark energy, find gravity gaining the upper hand. We don't know which way that will go. The honest answer from the data is that we're in the middle of one of the most uncertain periods in cosmological history when it comes to understanding the long-term fate of large-scale structure. What we know today is our galaxy is moving toward the Great Attractor. The Great Attractor is itself moving toward Shapley, and the Dipole Repeller is pushing everything from behind. The race between gravity and expansion is still playing out, and we are, quite literally, in motion. There's something almost poetic about the Andromeda collision in this context. In 4.5 billion years, the Milky Way and Andromeda will collide and merge. Stars won't physically crash into each other. The distances between them are too vast, but the gravitational interaction will fling stars into new orbits, reshape both galaxies entirely, and produce a single massive elliptical galaxy that astronomers have already nicknamed Malmquist. That future galaxy will be moving through space just as our Milky Way is moving today, still caught between the pull of the Great Attractor and the push of the Dipole Repeller, still embedded in Laniakea, still part of the same cosmic flow we're part of right now. The forces acting on us aren't going anywhere. The cosmic web doesn't dissolve on human or even stellar timescales. The push and the pull will outlast the Earth, outlast the Sun, outlast the Milky Way as we know it. They are features of the universe at a scale where even the death of stars is a local detail. To fully understand what the Great Attractor and the Dipole Repeller are, you need to zoom out one more time, because both of them are expressions of something larger, the structure of the universe itself. The universe is not a uniform sea of matter sprinkled with galaxies like grains of sand. It is a web, a cosmic web. Matter in the early universe wasn't perfectly smooth. There were tiny quantum fluctuations, variations in density smaller than any scale you can meaningfully imagine, imprinted across space by the physics of the moments just after the Big Bang. Over billions of years, gravity amplified these fluctuations. Regions slightly denser than average attracted more matter, growing denser still. Regions slightly less dense than average lost matter to their neighbours, growing emptier still. What emerged from this process, running for 13.8 billion years, is the structure we see today. Vast sheets and filaments of galaxies marking the densest concentrations, and, between them, enormous voids marking the regions that gave up their matter to build the surrounding structure. In this picture, the Great Attractor region isn't an anomaly. It's just an unusually prominent node in the cosmic web, a place where the network of filaments converges and concentrates a particularly deep gravitational basin. And the Dipole Repeller isn't an anomaly either. It's a void, one of the countless regions of the cosmic web that is defined by the absence of matter, the space between the filaments. Our galaxy happens to sit on the edge of one basin, adjacent to one of these voids, pulled from one direction and pushed from the other. If we had formed somewhere else in the cosmic web, in the middle of a denser region, or deeper inside a void, our peculiar velocity would be different. The forces shaping our motion would be different. Where we are in the cosmic web is as fundamental to our nature as our position in the Milky Way, or the Milky Way's position in the local group, and most people have no idea this layer of the address even exists. But here's what makes the cosmic web even more remarkable than the structure itself. We can trace its origins back to the very first fractions of a second after the Big Bang. The fluctuations that seeded the cosmic web aren't random noise, they're imprinted by physics. In the early universe, matter and radiation formed a hot plasma, and pressure waves, acoustic waves, propagated through it at roughly half the speed of light. These waves had a characteristic scale, the distance a sound wave could travel before the universe cooled enough for matter and radiation to decouple, about 380,000 years after the Big Bang. That scale is roughly 490 million light-years in today's expanded universe. It's called the Baryon Acoustic Oscillation Scale, or BAO, and it shows up as a faint preference in the clustering of galaxies, a slight excess of galaxy pairs separated by that exact distance baked into the structure of the universe as a frozen echo of the early plasma. The voids of the cosmic web, including the region around the Dipole Repeller, are the negative imprint of this process. where the sound waves compressed matter, you get seeds of future clusters and filaments. Where they rarefied matter, you get the seeds of future voids. The largest voids in the universe today are the gravitational descendants of the lowest density regions in the primordial plasma, amplified over 13.8 billion years of gravitational evolution. Simulations of this process, like the illustrious TNG simulation at the Max Planck Institute and the Millennium simulation before it, reproduce the cosmic web with striking accuracy. You can run the physics of the early universe forward in a computer and arrive at something that looks almost identical to the maps astronomers have built from actual galaxy surveys. The voids are in the right places, the filaments connect the right nodes, the clusters form where the overdensity is predicted. The statistics are staggering. Roughly 80% of the observable universe's volume consists of voids, 80%. The filaments, walls, and clusters that we tend to think of as the universe, the things, occupy only about 20% of the space. The other 80% is the structured emptiness of the cosmic web's void cells. The universe is mostly nothing, and that nothing has a shape. Here's something that's been sitting at the edge of this story, and I'd be doing you a disservice if I didn't bring it up. Not everything in the peculiar velocity picture fits neatly together. There's a phenomenon that a team of astronomers, led by Alexander Kashlinsky at NASA, announced in 2008 and called dark flow. A claimed detection that enormous numbers of galaxy clusters, spread across billions of light years, all appeared to be moving coherently in the same direction, not just local clusters in our corner of the universe, but clusters from across the entire observable universe, all drifting together. If dark flow is real, it would not be explainable by anything inside our observable universe. The Laniakea Basin, the Shapley Supercluster, the Dipole Repeller, none of these could produce coherent motion on that scale. The only explanation that's been seriously proposed is that dark flow is being caused by some massive concentration of matter outside the observable universe, beyond the boundary of what we can see, pulling on everything we can see from across a distance so vast it lies beyond the cosmological horizon. This is where the story gets genuinely strange in a way that has no clean resolution. The dark flow claim has been highly contested. Subsequent analyses of Planck satellite data in 2013 found no evidence for it. Other teams have found weak supporting signals. The debate is not settled. Dark flow may be a real signal, or it may be a systematic error in the analysis, or it may be a subtle artifact of how you choose to measure the CMB. But here's the thing, if it's real, it means the forces shaping our galaxy's motion don't stop at the edge of what we can observe. It means there's structure beyond the observable universe, mass distributions, voids, filaments, that we will never be able to see, but whose gravitational influence can still reach us. It means the Great Attractor story doesn't end with Laniakea, it might not end at all. And the specific way Kashlinsky's team found the signal is worth understanding, because it illustrates just how difficult this kind of measurement is. Their method used galaxy clusters as test particles. Galaxy clusters contain large amounts of hot gas that leave a faint imprint on the CMB as photons pass through them, an effect called the kinetic Sunyaev-Zeldovich effect, or KSZ. If galaxy clusters are all moving coherently in one direction, that bulk motion would produce a systematic KSZ signal across the full catalogue of clusters. Kashlinsky's team built a catalogue of hundreds of clusters, extracted their KSZ signatures from WMAP data, and found a coherent signal pointing in a consistent direction across the entire sample, regardless of where in the sky those clusters were located. That last detail is the key. If the signal were just a local effect from Laniakea or the Great Attractor, it would be strongest for nearby clusters and would average out for clusters spread across the full observable universe. What they claimed to find was a signal that didn't diminish at large distances, something that was equally present for clusters billions of light years away. In 2020, Kashlinsky's team revisited the question using Planck data, the successor to WMAP. with more precise temperature measurements and a larger cluster catalogue. They published a paper reporting that the dark flow signal was still present, still significant, and pointing in a direction broadly consistent with their 2008 findings. The physics of what this would imply is genuinely mind-bending. Our observable universe is roughly 93 billion light-years across. Anything outside the cosmological horizon, the sphere beyond which light hasn't had time to reach us since the Big Bang, is in principle undetectable through light or electromagnetic radiation. But gravity is different. Gravity isn't a signal that travels through space. It's a warping of space-time itself. A sufficiently massive structure beyond the horizon could theoretically be influencing everything inside it gravitationally, even though we could never observe it directly. Some theorists have proposed that dark flow, if real, could be evidence for a landscape of cosmological conditions beyond our horizon. Different regions of space with different densities, different expansion histories, possibly different physical constants. The multiverse by another name, or something equally strange. The signal is too contested to draw that conclusion, but the question it raises won't go away. And there's a deeper issue lurking here that doesn't get discussed enough. Our entire framework for cosmology, the standard model, the cosmological constant, the assumption that the laws of physics are the same everywhere, is built on observations confined to our observable universe. We can't see beyond the horizon. We can't confirm that the assumptions we make about the universe's initial conditions apply universally. Dark flow, if it's real, would be the first crack in that assumption. The first hint that something outside our bubble of space is influencing what happens inside it. Most physicists think that crack isn't there, that the Planck null result is correct, and the dark flow signal is noise. But the fact that Kashlinski's team keeps finding the same signal in improved datasets means the question can't be closed yet. Science requires that you follow the data, not the consensus, when the two diverge. And right now, on this specific question, they haven't fully converged. Let me pull back one more time and think about what we've actually established here, because I think the full picture is more remarkable than any single piece of it. Our galaxy is moving at over 1 million miles per hour. That motion has a cause. Two causes, actually. A gravitational basin we're falling into, Laniakea, anchored by the Great Attractor, extended further by the Shapley Supercluster, and an underdensity we're being pushed away from, the Dipole Repeller, a vast void on the opposite side of the sky, contributing as much to our velocity as the attractor itself. This push-pull model was established only in 2017. Before that, the standard assumption was that our velocity was primarily pull-dominated, that we were being drawn toward the Great Attractor, with most of the acceleration accounted for by the mass concentrations in that direction. The Dipole Repeller showed that this was at best half the story. There's a philosophical implication in that which I keep coming back to. We spent 40 years focused on what was attracting us. We built increasingly detailed maps of the dense structures in one direction of the sky. We identified cluster after cluster, supercluster after supercluster, each one contributing its gravitational piece to the puzzle. And all along, an equal and opposite force was operating on us from the other direction. A void defined by emptiness, doing as much work as all those billions of solar masses combined. The emptiness of the universe isn't passive. The voids aren't just the spaces between the structure. They are part of the structure. They shape it. They drive galaxy flows. They push as the clusters pull. In the cosmic web, the empty cells are as important as the walls and filaments that bound them. The nothing is doing something. This is what makes voids worth studying, not just because they're empty and that's philosophically interesting, but because the emptiness is dynamically active, it has effects, it has influence. It shapes the path of galaxies across hundreds of millions of light years. The universe is made as much of its absences as its presences, and our own motion through space, the particular way our galaxy happens to be moving at this particular moment in the history of the cosmos, bears the fingerprints of both. But I want to push that philosophical point into something more concrete, because the implications of the push-pull model go beyond how we think about our own galaxy. Before the Dipole Repeller, the standard approach to peculiar velocity cosmology was fundamentally one-sided. You identified overdensities, you measured their masses, you computed the gravitational pull on the local group, you compared it to the observed velocity, and you tried to close the budget. This approach had been struggling for decades. The numbers never quite added up. There was always a residual velocity that the known attractors couldn't fully explain. The introduction of the repeller side of the equation didn't just explain the residual, it changed the entire conceptual framework. The velocity field isn't just a map of where mass is, it's a map of the difference between overdensities and underdensities, the contrast between the dense and the empty, integrated across the entire volume around us. You can't understand our motion by looking at one side of that contrast. You have to look at both. This realization has opened up what's now called void lensing and void galaxy cross-correlation as active tools in cosmology. By measuring how galaxies move around known voids, astronomers can extract the density contrast of those voids with much higher precision than before. That constraint feeds into measurements of dark energy, of the growth rate of structure, of the total matter content of the universe. Voids have gone from being the empty spaces between the interesting things to being precision cosmological instruments. The 4MOST Hemisphere Survey, expected to deliver its first full results in the late 2020s, is specifically designed to build the most detailed peculiar velocity catalogue ever assembled. Hundreds of thousands of galaxies with precise distances and velocities, covering both hemispheres of the sky. When that data is combined with Wallaby and DESI's galaxy catalogues, the three-dimensional velocity field model of our local universe will be refined to a precision that makes the Cosmic Flows 3 catalogue look like a rough sketch. The Dipole Repeller's true shape and contribution will likely change. There may be additional repellers that we haven't identified yet. Every refinement of the model is a refinement of our understanding of where we are, of what's pushing us, of what's pulling us, and of how precisely our position in the cosmic web determines everything about how we move through it. There's one more dimension to this that I want to highlight before we move to the final picture, because it touches on something fundamental about how science actually advances. For most of the 20th century, the study of large-scale structure was dominated by the question of what exists, cataloguing galaxies, mapping their positions, measuring their distances. That was the primary project, the three-dimensional map of the universe. The Laniakea and Dipole Repeller work represents a shift to a different question, not just where things are, but what they're doing. The peculiar velocity field encodes information that the position field doesn't. Two galaxies at the same position but with different velocities are in completely different gravitational environments. Measuring both, position and motion, gives you a far richer picture of the underlying structure than either measurement alone. This is why the next generation of surveys isn't just going to build bigger galaxy catalogues, it's going to build bigger velocity catalogues, and the scientific returns from those velocity maps, in terms of constraining dark energy, measuring, the growth of structure, testing general relativity on cosmological scales, may turn out to be larger than anything the position-only surveys produced. The Dipole Repeller isn't just a fact about our cosmic neighbourhood, it's proof of concept for an entirely new way of reading the universe. We've come a long way from that opening question. What's pulling our galaxy at 1,000,000 miles per hour? Let's map what we actually know. In the late 1970s, astronomers detected a massive anomaly in galaxy peculiar velocities pointing toward an invisible region behind our own galaxy. They called it the Great Attractor. For a decade, the only thing they could measure was its gravitational shadow, the way it bent the paths of hundreds of thousands of galaxies without being visible itself. In the 1990s, X-ray telescopes pierced the Zone of Avoidance and found the Norma Cluster, Able 3627, sitting at the heart of the anomaly. A massive galaxy cluster, one of the largest in our neighbourhood of the universe. But the Norma Cluster wasn't massive enough alone. The Centaurus Supercluster surrounding it wasn't enough. Even adding the Shapley Supercluster, the most massive structure within hundreds of millions of light-years, still left a gap between theory and observation. Then, in 2014, the Laniakea discovery reframed the whole picture. We're not being pulled toward the Great Attractor from outside. We live inside a gravitational basin called Laniakea, of which the Great Attractor region is the centre. Our motion is the motion of a galaxy on the rim of this basin, flowing inward. And then, in 2017, the final piece. A vast underdensity on the opposite side of the sky, the Dipole Repeller, contributing as much to our peculiar velocity as the attractor itself. Half pull, half push. Balanced forces from opposite directions combining to drive our galaxy along its path through space. And sitting beneath all of it, the cosmic web, the large-scale structure of the universe, built by 13.8 billion years of gravity working on quantum fluctuations, producing a pattern of filaments, sheets, clusters, and voids that shapes everything from the motion of galaxies to the formation of stars to the fundamental question of where we are and how we got here. There's one more thing worth saying before we close. All of this happened in the last 50 years. The Great Attractor wasn't discovered until the late 1970s. Laniakea wasn't mapped until 2014. The Dipole Repeller wasn't identified until 2017. The Vela Supercluster was found the same year. The Zone of Avoidance is still being mapped. The dark flow debate is unresolved. We are right now in the middle of working out the large-scale structure of our cosmic neighbourhood. The story isn't finished. The model isn't final. There are almost certainly structures, attractors, repellers, voids, superclusters that we haven't found yet, hiding behind the Zone of Avoidance, or simply too diffuse to have detected with current instruments. Every new survey, every new telescope, every new technique for piercing through the galactic dust brings another piece of the picture into focus, and every time we look, we find that the universe is more structured and more empty than we thought. The field that's emerging from all of this has a name: cosmic cartography. It's the systematic project of mapping the large-scale structure of the universe, not just in terms of where galaxies are, but in terms of what those galaxies are doing, how they're moving, where they're flowing, what the underlying gravitational field looks like across the full three-dimensional volume around us. For most of astronomical history, we mapped the sky in 2 dimensions. We measured positions, right ascension, declination. Adding the 3rd dimension, distance, required measuring redshifts, which is painstaking but doable. But adding the 4th dimension, peculiar velocity, the motion beyond what expansion predicts, requires something harder still: independent distance measurements. You need to know where a galaxy truly is, not just where the expansion of space places it. The most reliable methods for this are the Tully-Fisher relation for spiral galaxies, the relationship between a spiral, galaxy's rotation speed and its intrinsic luminosity, and the fundamental plane for elliptical galaxies, a 3-way relationship between size, luminosity, and velocity dispersion. Both methods give distances with uncertainties of around 20%, not perfect, but good enough to extract peculiar velocities statistically across large samples. The Rubin Observatory's legacy survey of space and time, beginning its full operations in the mid-2020s, will photograph the entire southern sky repeatedly over 10 years, building a time series record of billions of objects. Among its scientific programs is an attempt to extract peculiar velocity information from galaxy morphologies and photometry at a scale that has never been possible before. The resulting dataset will likely transform every branch of large-scale structure cosmology, including everything we've talked about in this video. There's also a prediction sitting inside the current push-pull model that hasn't been tested yet. If the Dipole Repeller is correctly characterized, then galaxies on its far side, galaxies that are beyond the void rather than on our side of it, should show peculiar velocities pointing away from us, accelerated outward by the same void repulsion that's accelerating us in the opposite direction. Testing that prediction requires observations of galaxies in one of the most observationally challenging regions of the sky. But it's testable, and in science, a testable prediction is the beginning of the end of uncertainty. The model will be proven, refined, or overturned by data. That's how this works. And the fact that there's still something to prove, that the story isn't finished, is, I think, the most exciting thing about it. Think about where you are for a moment. You're on a planet orbiting a star. The star is one of 400 billion in a galaxy. The galaxy is one of a few dozen in the local group. The local group is one cluster in the Virgo Supercluster. The Virgo Supercluster is one lobe of a gravitational basin called Laniakea. And Laniakea is moving, right now, at over 1 million miles per hour, because a massive concentration of galaxies hundreds of millions of light years away is pulling it forward, and because a vast emptiness on the other side of the sky is pushing it from behind. You live inside the gravitational influence of the Great Attractor. You live on the edge of the Dipole Repeller, and the fact that those two things are roughly balanced, that the pull and the push are working against each other with nearly equal force, is not a coincidence. It's a direct reflection of where you happen to be in the large-scale structure of the universe. A specific position in the cosmic web, with its particular combination of dense neighbours and empty neighbours, producing the particular motion that our particular galaxy happens to have at this particular moment in cosmic history. You are not in a random place. Your address in the universe is precise, and the forces that come with that address have been shaping your galaxy's journey through space for billions of years before the Earth even existed. The universe is bigger than you think, and most of it, the part that shapes the biggest structures, is nothing at all. If this is the kind of story you want to keep following, consider subscribing. Every video on this channel is built around the same question. What do the places we can't see tell us about the universe we're in? The voids, the shadows, the things hiding behind the dust. That's what Void Observatory is for. The next chapter is already coming.